I'm the manager of power, fossil fuel, alternative energy and storage at the ASEAN Center for Energy. I'm also the team leader on the development of our flagship study, the ASEAN Interconnection Master Plan Studies. Brief intro, the ASEAN Interconnection Master Plan Study set out the transmission infrastructure needed to support multilateral power trade in the ASEAN and renewable energy integration into the ASEAN power grid. The work received generous support from the USA through its Clean Power Asia program. And following the endorsement of the ASEAN Interconnection Master Plan Study about 2 weeks ago at the 39th ASEAN Minister on Energy meeting, we are continuing the study and expand it to cover more issues, including to assess the impact of our regional power grid to improve the air quality. Hence, we are very pleased to collaborate with the expert from NREL and also from University of Minnesota. Again, and there's a continuous generous support from the USAID to quantify the impact of renewable energy development on air quality and human health in Southeast Asia. So today we will have this webinar and welcome everyone to join. But before that, let me invite Scott Bartos, a regional energy advisor at USAID Regional Development Mission for Asia, to share also a few words. And I would like to personally thankful for Scott and his support. Scott, over to you.
Thank you, Benny, and good morning, friends and colleagues from Bangkok, Thailand. So again, my name is Scott Bartos. I am the Regional Energy Advisor here at USAID's Regional Office for Southeast Asia. It's really a great pleasure and an honor to continue and expand on our work with ACE and with NREL. As Benny noted, we've been working together on the AIMS-3 project, and this topic of air quality is one that is very near and dear to my heart, and trying to also be able to kind of understand and communicate the benefits of our energy sector work, especially with the focus on clean energy technologies. What are those benefits to human health and the environment? How can we better quantify and describe those benefits? Has been a passion of mine, but it's been a passion that has been challenging to kind of get my brain around. For those of you who know me, I worked before coming to our office in Bangkok. I was based in USAID's Vietnam office in Hanoi. And I know while there, I worked on a working group, an embassy working group, looking at air quality issues in Hanoi and in Vietnam, which are often quite challenging, often in code red, code purple air quality states for weeks on end. And as a member of that working group, it was a very active debate, discussion around why was the air quality so poor at many times of the year there in Hanoi. And to be honest, I think that working group, even though we gathered available information that we could identify and could locate, we were still left with probably more questions than answers. And so for that kind of one of my personal reasons, but I know that this is a challenge not only in Vietnam, but across the region, I'm very happy that we're now kind of beginning to take a closer look and think about some of the key sources of air pollution across Southeast Asia. And this is just taking a look at one slice of that, one of the stationary sources. I know there are many contributors from transportation and agricultural activities, but at least in this one case, in this one slice of the pie, I am optimistic we'll have a much better understanding of the contributions, as well as, again, being able to communicate and understand the benefits of the range of clean energy work that USAID and our partners are doing in the region. Before I hand it off to my friend Garvin, again, I mentioned that this is a kind of a personal passion. By way of further introduction, before joining USAID, I worked at the Environmental Protection Agency out of Washington in the Office of Air and Radiation. And so have kind of, a fairly deep background on air quality and climate change issues. So it's really wonderful to kind of join forces again with my old colleague Garvin Heath when we worked together back in the late 90s at EPA to kind of cross paths again on this exciting project. So with that, let me hand it off to Garvin. Again, thank you everyone for joining us for this introductory workshop on the topic. And thank you very much to Benny and his team at ACE, as well as the experts at NREL for helping us to kind of, again, get our brains around what are the impacts and benefits related to clean energy technologies for Southeast Asia. Thank you.
Hi, I'm Garvin Heath, and thank you very much for the introduction, Scott, and the welcome from Benny. It's our pleasure at the National Renewable Energy Laboratory to have such a strong partnership and to have the opportunity to work in the region of Southeast Asia, apply for the first time, I think, an exciting new model that's being developed by our colleagues at the University of Minnesota, and to pull that all together to a study that's focused on the power sector transformation, and in particular the AIMS-3 scenarios that have been developed in order to understand the interconnection and variable renewable energy integration possibilities in the region, so that we can then be able to quantify the potential human health and air pollution benefits from doing so. I'm an air quality engineer by training. I have a PhD in air quality engineering, and I'm not the developer of this particular model that we're going to use, but have quite a deep background in air quality, and like Scott mentioned a couple decades ago in the U.S. Environmental Protection Agency in the Air and Radiation Office. So I'll be moderating, both speaking and moderating this workshop. This workshop is intended to give an introduction to the study that we've scoped with the support of USAID and our partners at ACE. And we welcome feedback and questions. Your questions and feedback will be important for us for really understanding the context in which this study is going to be applied. And of course, with COVID, we don't have the opportunity to travel to your region to understand that better and meet some of the stakeholders in the region. So these workshops are really our way of trying to connect to all of you in the region and your understanding of the AIMS-3 scenarios and the challenges in the region, of data sources and other factors. We are happy to take questions if needed along the way. We also have reserved time at the end of each of these 4 different sections within our agenda for some question and answer. If you want to not forget your question, you can write them down in the chat feature within this Zoom meeting, and we'll get to them at the end. And if you think that's a question that would be best answered more immediately, then maybe indicate that in the chat as well. If anyone does happen to enter a question into the question and answer function, we have our facilitator, Karen Wadsock, who will be then transferring it into the chat just so it's in one place and everyone can follow. So I will be providing an overview of the study and the context. I will also, then turn it over to our colleagues at the University of Minnesota, Professor Jason Hill and Dr. Sunil Thakrar, to discuss the methods and in particular the model that they've been developing that will be applied for the first time in this study. There are some important questions about how do we translate the AIMS-3 scenarios into the required inputs to an air quality model, which I'll discuss in the 3rd section. And the 4th, shorter section will just be a wrap up and mentioning of a few next steps, and open again for further discussion with our participants. If we run right up against time, and if anyone has some additional questions, I can certainly stay afterwards through the Zoom platform and continue the dialogue. And we'll be providing some contact information at the end for you to reach us. So let's go to the next slide, Karen. Okay, so we're now entering the first part, the overview. So this is our objectives here, as I think Scott mentioned and Benny alluded to as well, are to estimate the air quality and selected public health benefits from the AIMS-3 scenarios that have already been developed through 3 phases of a study that NREL has been a part of, but hasn't led, and we're receiving information from those that led the AIMS-3 study about these scenario results for the power sector. In analyzing the AIMS-3 scenarios, we want to quantify the linkages between air quality and public health, and in particular in the context of renewables integration to the grids across the ASEAN countries to inform regional planning as well as country-specific planning, policy making, and regulatory decision making. And in doing so, we're applying a first of its kind, we think, and we hope you will think, very user-friendly global air quality model to this example energy transition topic in Asia, and to raise awareness of the model's capability for future decision-relevant studies. And that's something we'll mention at the end, and hopefully you'll get a feel for when we discuss the model in the methods section. The audience for this study are the ACE research staff who we're already collaborating with, but I know that there's many more that maybe are attending this workshop and might be interested in this work, to the members of the heads of the ASEAN Power Utilities, HAPUA, and other interested energy and air quality policy stakeholders within the ASEAN member states. And I hope that many from these audiences and possibly from some others are attending this workshop, and one more that we have planned at the end, near the end of the study. Our deliverables, this is just in summary, we'll go over more of these details later, but our deliverables are training activities and materials, including the workshop today, and then a technical report that's co-authored by NREL, the University of Minnesota colleagues, and ACE. Next slide. So to provide some background that some of you, maybe many of you, are already familiar with, but to make sure that everyone kind of understands the context, a major effort that is updated, I believe annually, been going on for several decades, is an effort called the Global Burden of Disease, which quantifies for all regions of the world the sources of disease and also of deaths from global citizens. And it concludes that around 500,000 premature deaths are caused by poor air quality just in Southeast Asia. The latest year of these data and results is the year 2016. And it's important to note that Southeast Asia has one of the highest counts of premature deaths of any region in the world. The cause of these premature deaths from poor air quality is mostly from exposure to long-term exposure to fine particulate matter, what is often referred to as PM 2.5. The 2.5 refers to the size of the particle, 2.5 microns or less. They're so small that they go deep into the lungs, and with long-term exposure, meaning over years, at elevated levels, concentrations of fine particulate matter, that can lead to many serious health consequences that can ultimately lead to early death or premature death. Fossil fuel combustion is one leading cause of poor air quality and premature deaths, and the image to the right shows a very recent study published this year. Its title is Global Mortality from Outdoor Fine Particle Pollution Generated by Fossil Fuel Combustion. The study uses a different model that we will use here, a model called GEOSChem. But nevertheless, it shows, as you can see, the hotspots in the Southeast Asian region, as well as adjoining regions in South Asia and North and Central Asia. But really looking at the Southeast Asian region, you can see that it's quite varied across the countries, but it does have some particular hotspots and elevated excess deaths in many regions. Renewable energy, especially renewable power generation, can displace fossil fuel combustion for electricity generation, and therefore can potentially reduce the disease burden. And hopefully, if renewables are integrated with some speed, even in light of increasing demand, with increased population and increased economic activity. So this is the context and some background just on air quality, and in particular focusing on PM2.5, fine particulate matter, and its role in leading to one of the most serious health consequences, early death. Next slide. So our goal, to reiterate, is to evaluate the air quality and public health impacts of energy transition in Southeast Asia through a first study of variable renewable and grid interconnection cooperation scenarios for the ASEAN power sector. Those scenarios, of course, are coming from the study AIMS-3, which identified the interconnection infrastructure needed to integrate higher shares of renewables and enable expanded power trade across the ASEAN region and individual countries. 4 scenarios were created for the AIMS-3 study, and they're shown in the chart on the right. And they were modeled using both capacity expansion modeling software or approaches for the power sector, as well as power flow simulation, which is a more granular look at the both consumption and generation of power and the trade of power. The results of which will be analyzed using this global air quality model for the air quality effects and human health effects. And you can see on the right the increase in power generation capacity in gigawatts across those 4 scenarios, a base case and then 3 alternative scenarios: optimum renewable energy, ASEAN renewable energy target scenario, and a higher variable renewable energy target scenario for the years 2025 and the year 2040 across several different fuel types. Next slide. The expected outcomes from the study when it concludes are maps similar to that shown on the right from this recent study, except we will have even higher spatial resolution than this model, showing the degree and location, or the degree or magnitude and location of benefits from the 3 AIMS-3 alternative scenarios as compared to the base case. The 2 metrics that we will evaluate are the change in concentration of PM2.5, fine particulate matter, as well as the resultant change in premature mortality, with the expectation that as we increase renewable energy generation and decrease by share the fossil fuel generation, that we will have a reduction in premature mortality in comparison to the base case. We will have tabulated results that are summed for each country and each scenario to make it relevant for all of the ASEAN member states. We will interpret those results, for instance, which scenarios yield the highest benefits and in what magnitude, and for what reasons, for what displaced power generation source. We'll also have a summary of lessons learned from this analysis of the AIMS-3 scenarios and the application of this global INMAP model. This is the global air quality model that we will introduce in this workshop, with some suggestions about how this model can also be used in other geographic contexts, for instance, individual countries or other regions of the world, other sectors besides for the power sector, and to answer other research questions. We will also, at the end, be providing to stakeholders that, in collaboration with ACE, will be selected to have an introductory training on this global INMAP model. INMAP stands for Intervention Model for Air Pollution. And this model you will hear is one that is intended to be very much more user-friendly as far as its computational demands, computer platform and software demands, and training demands for the individuals using the model. So we expect a greater number of ASEAN member state experts will be able to use this model as compared to current state of the science models. Next slide. Many of you, I'm sure, are quite familiar with the AIMS-3 study and know very well about the different scenarios and how they're constructed. I am learning. I was not part of the AIMS-3 modeling team. Some of my colleagues have been involved, and so I'm learning about them. I won't spend time describing all the features that are described in this slide, but I think in short, what I wanted to say is that all three of the alternative scenarios, the optimum renewable energy scenario, the ASEAN renewable energy target scenario, and the high renewable energy case, all three of those scenarios will be evaluated and compared to the base case, adhering as best as possible to the definition of these scenarios in the AIMS-3 study. Next slide, please. The timeline for the study is that we've already been working pretty intensely with our ACE colleagues and also with the University of Minnesota on developing the input data that's required to provide to the air quality model to then complete the modeling. This is expected to be complete, as well as the air quality modeling itself, by the end of March of 2022, next calendar year. We have webinars and workshops planned. The first one, of course, is today. The next one will be somewhere in the February to April 2022 timeframe. We expect that to be a multi-part workshop, one part being a presentation and discussion over the results, a second part being the training on the global INMAP model. And then we will have a technical report complete by June or the end of June 2022, including, we hope, the feedback that we can incorporate and address from the interactions that we have at these workshops, as well as other interactions that we might have along the way. Next slide, please. So we'd planned to break, actually go back one, Karen. We'd planned to break at the end of each of these sections of the workshop today to take any questions that anyone might have. I have the chat open. I'm not seeing any that are typed in at this point. If someone wants to raise their hand and ask a question verbally, we have time for that. I'll leave a moment for you to decide if you want to type one in or raise your hand. Okay. Well, we can proceed then to the methods, and certainly type your questions as you have them, and we will get to them as soon as we can. We'll proceed to the methods now. I'll be giving the introductory slide and then turning it over to my University of Minnesota colleagues. So next slide, Karen. Thank you. This is just an overview of the steps that are used within an air quality modeling study, and in particular, the steps that have been programmed into the Global INMAP model. Global INMAP, again, stands for the Global Intervention Model for Air Pollution, which was first developed at the University of Minnesota and then with collaborators at the University of Washington, and additional work now being done at the University of Illinois, as the model has been continued to be adapted, developed, and applied in many different settings, focused on the United States. This model is now being expanded to a global, so not just the United States boundary, but now a global boundary. And you'll learn more about that. The basic steps are, as you can see in the diagram, and it starts with emissions. Here we have to develop the emissions inventory, it's called, by adapting or translating the AIMS-3 scenarios of the usage, the generation of different power sector fuel sources, fossil fuels, biomass, if possible, with data, and renewables, and translating that into emissions of the pollutants that can form particulate matter in the atmosphere, which is the focus of the global INMAP model. So NREL is leading the, the development of that emissions inventory. We have had active and very fruitful involvement and input from the ACE team that we're collaborating with. And this will be also done in conjunction with the University of Minnesota colleagues to ensure that what we are developing is exactly what the global INMAP model needs as data inputs. The next steps generally for any air quality model, and in particular for the global INMAP model, are to use the model formulation to then estimate concentration. So this is a concentration of PM2.5, fine particulate matter. In particular, it's a change from a baseline scenario, not the business as usual scenario, the base scenario from the AIMS-3 study, but another global baseline scenario. And that's how the model is programmed. Concentrations, in order to affect health, have to interact with people. So people are spatially distributed, and we need to understand where people live in order to understand what their exposure to concentrations are. Concentrations exist in the atmosphere, and it's only when people interact with those concentrations are they then exposed to the particulate matter. When they're exposed for a long period of time, a long-term average concentration of PM2.5, that's what can lead to the health effects that we're focusing on in this study. Some health effects are from short-term exposure. Those are not included in this model. We're looking at the long-term exposure. And so in this model, we are then going to be able to estimate, as I described before, premature or early deaths that result from long-term exposure to PM2.5. There are other steps in the domestic INMAP model, which can include assigning a monetary value to the deaths. It's through a metric called the value of statistical life. That's not going to be available for this study globally, so across the ASEAN region. So we stop at health effects, which is just the count of deaths. In the United States, with the INMAP model, we can do economic damage, and it's also been used in the application for environmental justice. If we remember back to the exposure, we have to know where people live. If we understand who is living where and how that can differ in terms of the location, then we can evaluate if there are any overdue burdens to one segment of society versus another. For instance, by income group, or for instance, by race, or other demographic factors. That's how the study can be potentially extended in the future in the global context. We're stopping at health for this study. So as this is the overview of just the general steps, let me now turn it to my University of Minnesota colleagues. We'll start with Professor Jason Hill, who I've known for a very long time and is one of the original developers of this model, who will then introduce his postdoctoral student when he hands it over to him.
Wonderful. Thank you, Garvin. Good morning, everyone. I'm not sure, is my video showing here, or are we still on you, Garvin?
Mm-hmm.
Are you able to see me? Okay, wonderful. Thank you. Yes, good morning, everyone. I'm Jason Hill. I'm professor in the Department of Bioproducts and Biosystems Engineering at the University of Minnesota. And I work on assessing the environmental impacts of food and energy. And I look at impacts on climate change and air quality primarily. The work that we're going to describe today uses this INMAP model, which was developed back in, almost a decade ago. Development of that began with my colleagues Julian Marshall and Chris Tessum. And since then, we've applied the model to dozens of different applications. And I was very fortunate a few years ago to begin working with Dr. Sunil Thakrar, who will be presenting here. Sunil came from University of Oxford as a graduate student to work in my group. And as one of his chapters of his dissertation described the initial development of global INMAP. This is exactly the sort of application that we were hoping for in the development of global INMAP, applying what we know about air quality and its impacts to a global context. So with that, I will turn it over to Dr. Thakrar, who will describe the model and its intended application in this project.
Thanks, Jason. It's great to be here. Hello, everyone. So as Garvin and Jason mentioned, I'm going to talk to you about global INMAP, which is an air quality model. And that means it estimates how changes in emissions can affect pollutant concentrations across space. And that's, of course, important because Garvin was telling you that there are 500,000 deaths each year associated with exposure to air pollution in Southeast Asia. And if you want to improve the air quality by targeting emission sources such as power generation, then you're going to want to know what those effects will be. And for that, you need models. So there are two types of air quality models: chemical transport models and reduced complexity models. The slide that Garvin showed earlier, the Vora et al. Study, uses a chemical transport model, GeoSChem, which I'm going to be talking about a little bit. And these models are notoriously difficult. They're literally simulating the atmosphere. And generally, they require supercomputers. They require a team of experts, usually at the PhD level or, of course, higher. And they require days to weeks of simulation time for just one policy scenario. So you can see here at the bottom, here's a map of all the known users of GeoSChem, the state of the science chemical transport model. And you can see that there are countries where there are lots and lots of deaths from air pollution, where there simply are no known users of this model GeoSChem, suggesting that the demands of air quality modeling are much higher than the resources available to run them. Now, there is an alternative, these reduced complexity models, one of them being INMAP. These are far less resource intensive and they're far easier to use. In fact, you certainly don't need a PhD to run a reduced complexity model. They come at the expense of some accuracy, but the big downside is generally these have only been available for the United States, which is comparatively a very clean country in terms of the air quality. It only has 4% of the world's population and only 2% of the air quality related deaths. So what we did, as Garvin and Jason mentioned, is we developed global INMAP. Basically, we took a United States reduced complexity model and we applied it to a global scale. So how did we do that? So basically, we kept the same modeling assumptions as the INMAP model for the United States, but we allowed global inputs to be used. So that includes weather, meteorological variables such as temperature, which are needed for an air quality model, and also uses outputs from a chemical transport model in order to get the chemistry and the physics of the model right. And one feature of INMAP is it actually has a high resolution computational grid. So typically these types of air quality models are run across different grid cells. The pollution is evaluated at each grid cell. And InMap has a variable resolution grid. So it has 170,000 ground level grid cells, and the grid cells vary in size depending on whether you're in an urban location, in which case there's higher detail, or a rural location where there's slightly less higher detail. So for InMap, the grid cells vary in size from 4 to 500 kilometers in length. So we can run global InMap, and here are some results. So what you see is when you run InMap at the global scale, just looking at all emissions, that it can produce estimates of surface level PM2.5 concentrations, the pollution concentration. And the spatial path, the results generally reproduce those done by a state-of-the-science chemical transport model, as you can see here on the left. So when you run GeoSchem, same model that takes a longer time, you get a similar answer. And if you zoom in, so you can also get these changes in pollutant concentrations at the urban scale. So here, this is a simulation where we take changes in emissions from transport. So we ask the question, okay, what if the transport emissions were higher globally? Then we can run these models on the changes in emissions and estimate the changes in pollutant concentration. So here we've zoomed in on a global simulation, just looking at Cairo, Egypt, which is the largest city in Africa. And you can see here is the change in emissions. And here is how GeoSchem does with estimating the changes in concentrations. So you can see that the concentrations are higher when you increase emissions from transport. They're about 0.25 micrograms per meter cubed higher all across this area. And for InMap, you get a similar answer. But because the resolution is much higher, you can see how, you can see with an InMap simulation on the same emissions that the concentrations are much higher, so the air is much dirtier in the Nile Valley. And so you have this urban scale fidelity. So InMap is a global scale model, but it has this urban scale resolution. So not only has global InMap got a higher resolution than most global models, it is also much faster. And in fact, when run on the same machine, this global InMap model is 96% faster than the standard global chemical transport model that I mentioned. And that's despite having 13 times the ground level grid cells and 39 times the population weighted average grid cell area. So another way of saying this is the average person in the world for a global InMap simulation lives in a grid cell the size of Tahiti. Whereas for a GeoSchem standard chemical transport model simulation, the average person lives in a grid cell the size of Taiwan. So for the average person, you can't get that much detail about how the pollution changes where they live and how dirty their air is that they're exposed to. But with InMap, you can get a lot more detail. So you can currently run global InMap and you can get changes in annual average PM2.5 concentrations, which is what is important for health, as Garvin was talking about. But really what you want to know is how many people are exposed to those changes in concentrations and how many more people face increased mortality risk, how many more people die. So currently we're adding this capability to the global InMap model. And in doing so, we're using demographic data. So basically you need to know where people live across space, and you also need to know their baseline mortality rates. And you need to use epidemiological relationships between pollution exposure and health. And so currently we're implementing this into the model to get estimates in changes in mortality for different policy scenarios. Okay, so that's global InMap. And now I want to ask the question, okay, how can we actually use this model? And thankfully, this model has been run for the United States quite a lot. In fact, it's been cited by over, I believe, 50 publications, including one published in prestigious international journals, such as Nature Communications or Science Advances. Here's one such study which used INMAP for the United States, looking at corn production. So corn production is associated with 4,300 deaths just in the United States each year. And what the study did was it ran INMAP on every single county that produces corn in the US, so thousands of counties. And it looked at how many deaths and where the deaths were from the emissions produced in each county. You can see for McLean County in Illinois, this is the result from running INMAP on the emissions in that county. And you can see the change in concentrations, pollutant concentrations arising from those emissions. So a lot of people downwind of this county are exposed. And on this map, you can see the change in death. So you can see that a lot of the deaths are concentrated in cities many miles away, such as Detroit and Chicago. And so this is INMAP is very useful, and global INMAP will be very useful for linking these pollution sources, i.e. where the pollution is coming from, to who is being harmed. Now, another use of global INMAP that is to, because it's very high resolution and because you can run many scenarios at once, because it's it's much quicker than most models, is you can understand the impacts of emission sources in great detail. So there's a lot of information in this figure, but this figure essentially represents all the deaths from pollution in the United States. There are about 100,000 deaths each year, broken down by sector. So industrial and commercial sector is associated with 29,100 deaths. Transportation is associated with 29,000 deaths. Food and agriculture, 19,000 deaths. Residential emissions, 12,700 deaths. And electricity generation, 10,200 deaths. So we broke the deaths down, attributed them to all these sources, but then we went into great detail here, looking at the activities, the processes, and the pollutants. So here you can see electricity generation in the US is associated with 10,200 deaths. Most of that is from coal, like coal fuel combustion. And most of that, the deaths are from this pollutant, sulfur oxide emissions, 10,900 deaths associated with that. So this, as you can see, gives you great detail. And I invite you to think about what a figure like this would look like for Indonesia or other countries. You can imagine it would be different. And these are the kinds of questions that we hope global INMAP will be able to answer. So finally, I just want to ask, okay, here's this model. Now, who can use this model? Well, it's an open source model. All the data in the code is public. As I've been saying, I hope that you don't need a PhD to run INMAP. Hopefully, you could get by with a bachelor's or a master's to run this. Normally, with a chemical transport model, you need quite a lot of expertise. It can be run on a desktop computer for some simulations, especially for regional simulations. It's helpful to have some GIS skills to generate emissions data. All you really need is a shapefile of to know where pollution is coming, where the emissions are coming from, and how large the emissions are in order to generate INMAP results. As Garvin was saying, it can tell you the change in annual average pollutant concentrations, and we're working on the changes in mortality. So my hope is that global INMAP will be able to bridge the gaps with policy needs where existing tools are lacking or computationally expensive. So I welcome any questions on these methods and this section.
Don't see any in the chat, but again, if anyone wants to raise their hand. Oh, here we go. One question. Oh, good. We're getting a few now. Do you see them, Samil, or should I read them to you?
Oh, I see the questions. Yeah. So
okay.
Two people have asked about the climate change impact. And so this model is only actually for air quality related emissions. So it doesn't include the climate impact, but we have done studies where we looked at both the climate and the air quality impact. And so, where we model for different scenarios, we model using InMap how that affects how dirty the air is and how and the health of the people breathing that air in. But we can also in tandem look at the changes in CO2 emissions or something like that. So no is the answer.
Thank you for the questions. Again, if you want to raise your hand and speak, you're welcome to, or type them in.
So I have a question. What is the spatial and temporal output of this model? Is it an annually averaged product? So yeah, that's a good question. So yeah, the output, so InMap gives you an annually averaged change in PM2.5 concentration. So it doesn't give you it doesn't tell you how the pollution varies across the season or anything like that. And spatially, as I mentioned, so the spatial scale varies. So in cities, it's higher resolution, up to 4 kilometers.
Let me just add that before we go into the next question, Samil, that the temporal resolution is on purpose because the highest monetized damages from air pollution in terms of its health effects is from premature mortality. Premature mortality is driven by long-term exposure. Long-term exposure in the studies that have evaluated it being defined as annual average concentration. So the reason that InMap is oriented around the temporal resolution of annual is because of the most important, as defined anyway by monetary value, the most important air pollution health effect, and the biological reasons of why premature death is linked to the long-term exposure, not short-term.
Yeah, thank you, Gavin, for that. I see another question. So the input data will be annual emissions. How can we convert the annual emissions into a shapefile? And is the model free for everyone to use? Right. So to the second part, yes, the model is free to for everyone to use. It's open source. And for the first part of the question, so shapefiles basically contain 2 pieces of information. They tell you how big the emissions are, and they also tell you where the emissions are coming from. So if you know both of those things, then you can generate a shapefile using some kind of GIS tool. So this is something that so this is kind of the one piece of expertise that people need in order to generate the outputs. But typically this can be done with other open source tools such as QGIS, where you can manually build emissions shapefiles to put in the data of how big the emissions are and where they are in space. That's all the model needs. Okay, so I have another question. Hi, why is the InMap model significantly faster? What enables it to be both faster and at the same time more accurate? So just a clarification, it's not more accurate than a chemical transport model. It's actually less accurate, but it passes some. It does well enough for certain policy scenarios. And the other part of the question is, why is the InMap model significantly faster? So the reason why it's faster is it makes some more modeling assumptions. So it makes assumptions about it uses simplified chemistry and physics to get the answers that it gives. Yeah.
And I think it's important maybe to emphasize that the reason that the model is built the way it is not to substitute or to provide another model that can have state-of-the-science accuracy to predict air pollutant concentrations, but rather to fill the void in an air quality model in the global context that can answer questions faster and therefore can answer more questions in the same amount of time and effort with lower requirements on the user so that more people can ask those questions. And especially, I think it fits well into a public policy space where an agency or an NGO or a utility or another user might be wondering, what if we did this? What effect would it have? What benefit or disbenefit would it have? And you can get the answer to that question very quickly through this model, as opposed to having to run the only other available models in the context of many global regions, which are these very computationally intensive, very training intensive, very expensive models that are the chemical transport models, which are more accurate. But that accuracy may not be necessary to answer many questions that people have.
Garvin, may I add one more piece to that, please?
Yeah.
So accuracy is how well it resembles the actual atmospheric processes and the concentrations that come out. But InMap does have the advantage, and I think this may be this may be what whoever asked the question may have been referring to, was the high spatial resolution. So even though the predictive power overall may not be as strong as a chemical transport model, the ability to get high resolution output, especially in the areas of high population density, mean that in those areas it can more accurately depict the concentrations resulting from emissions in those areas. So there is, with any of these models, there are those trade-offs in speed, computational power, predictive power, spatial resolution, and so forth. The other thing that I want to mention that I think has been was mentioned in passing a few times is that Global InMap also models primary and secondary fine particulate matter. So primary that results from dust or combustion, and secondary that results from atmospheric interactions of nitrogen oxides, sulfur oxides, volatile organic compounds, and ammonia. And all that is important because in the US, over half of the anthropogenic and human-caused fine particulate matter in the atmosphere is from these secondary sources. And when looking at biomass production, coal use, and so forth, there's a high contribution of those sources to atmospheric particulate matter levels as a result of secondary fine particulate matter.
Thank you. So I think we have time for this last question to answer the last question that's been posted to the chat. Samil, you want to take that?
So the question was, what meteorological data sets are used for the model input? So they are, if you know the MERA-2, so it's the reanalysis based off of NASA satellite data.
Okay, thank you. Also publicly available?
Yes, publicly available.
Yeah, great.
But it's not needed, just to clarify, it's not needed for a user to download and process that information. That's already built into the model. All the user needs is, in order to run a scenario, is to know the emissions from that scenario.
Thanks for, that's important to clarify.
Okay, another question.
Okay, Karan, I think we can probably, is there one more question? Karan, why don't you switch the slide, and if there's one more question, we can answer. Is there one?
Sorry, yeah, there is one more question, which I can quickly answer, but I'll change out the slides in a second. So the question is, do we just select Sorry, one second, let me find it. Okay, do we just select the total number of deaths in that region
Next
that is
slide,
related
Karen.
to, for example, lung disease, not the general total deaths? So actually, yeah. So in the capability that we're adding to estimate mortality impacts, you will be able to estimate the impacts from different types of death. Yeah. Okay.
Okay. I would like to move on to the next section. Oh, we have one hand up. Is it a short question? We'll try to take a short question if Laman, is that right? Has the hand raised still. Oh, Lamai. Maybe the hand was dropped. Okay, let's go to the next session. Of course, if you want to type the question in, then we don't have to lose it and we can get back to you. So I encourage Lamai to do that. So we're now going to the session that's going to talk about the input data. And as I outlined initially, the emissions is the required input data, and it's, as Samil also reviewed. And so how do we translate the AIMS-3 scenario, power sector scenarios to the input data, what's called an emissions inventory? That's what this session is about. So next slide, please, Karen. Okay, so let's start with the basics. The United States Environmental Protection Agency, their definition of an emissions inventory, which is this input file that's necessary for the global INMAP model and all other air quality models, is that an emissions inventory is a database that lists by source the amount of air pollutants discharged into the atmosphere during a year or another time period. So there are three basic components to the emissions inventory. What pollutants are emitted, how much is emitted, and where and when these pollutants are emitted. And I'm going to come back to with a slide focused on each of these next to explain each of them and how we are planning to address answering the question of translating AIMS-3 power sector scenarios to each of these three components in next slides. The bullet here, that next bullet that says emissions inventory is one of the multiple inputs required, is true for most air quality models because of the way the global INMAP model, like the domestic US INMAP model before it, is programmed. It actually takes care of all the other inputs. Like Samil just mentioned, meteorological files are required. We need to know the wind direction, we need to know the wind speed, we need to know the temperature. But that's already included in the processing and programming of the global INMAP model. It's not required for the user of global INMAP. So it might be theoretically straightforward or conceptually straightforward to think about what, how much, where, and when pollutants are emitted. But this is actually the most time-consuming part of any air quality modeling study, not just for global INMAP, but GeoSchem and all the other US-focused air quality models and other air quality models in Europe and other places. Developing the emissions inventory can be the most time-consuming and challenging part. There are many pollutants to track. There are lots of different sources, each with their own emissions characteristics. If you are looking forward into the future, then you have to figure out how you're going to project those and many other factors. So next slide. So there's a basic equation that embodies the concept of emissions inventory. For every source that we want to calculate emissions, that's the actual input metric. Here we're using an example of kilograms per year of a particular pollutant. We'll go over what pollutants we're talking about later. It's an equation that's the multiplication of an activity times an emissions factor. In the case of power generation, the activity is expressed in megawatt hours, generation, and therefore the emissions factor has to be expressed if we want kilograms per year as kilograms per megawatt hour. So that if you have taken any engineering classes or otherwise, you will see that the units that are in the denominator of the emissions factor are the same units that are in the numerator of the activity, which would actually be activity per megawatt hours per year. And so the megawatt hours cancel, and then you get kilograms per year. So you have to complete this for every source. And also you have to complete this for every year that you're going to be doing the modeling for. So activity, again, refers to the generation by a power plant, or perhaps it's fuel consumption. It sometimes depends. The emissions factor is then the mass of the pollutant that's released during the combustion to produce the energy. So for example, you might have NOx, which is nitrogen oxides, that are emitted. Let's take it as an example, kilograms, from gas combustion, natural combustion of natural gas in a power plant. Might be in the units of MCF. Or we might have SOx, sulfur oxides, that are emitted from diesel fuel that's burned. All of these are examples then of emissions factor, kilograms per gallon of diesel fuel, or kilograms per MCF of gas, or kilograms per megawatt hour of generation. Those will be all the emissions factors. They multiply by the same activity. So the gallons of diesel fuel, the MCF of gas, or the megawatt hour of generation, and then you can get to emissions. So next slide, please, Karen. There are different approaches to use to develop an emissions inventory. The simplest, from our perspective, is from the data perspective, obtaining the data anyway, if it's available, is if we were able to obtain this data from a continuous emissions monitoring system. This is abbreviated CEMS, and CEMS is an automated process that directly measures the emissions of the different pollutants. So if you remember back to the prior slide with the equation, that's directly the attribute, the characteristic that we're looking for in the inventory. It's emissions, kilograms per year. Typical pollutants that are measured from CEMS systems in power plants are NOx, SOx, and CO, CO being carbon monoxide. The uncertainty is rather low because you're directly measuring the attribute of interest. But not all plants or countries have CEMS required. And in fact, where we've looked with the assistance of ACE about where CEMS requirements exist in the ASEAN region, those data unfortunately are not made public. So although we would like to use a continuous emission monitoring system data for our emissions inventory, it's not available to us as far as we know right now. A second approach would be to take emission standards. These are regulations that are set by individual countries, sometimes within country regions or even municipalities. But let's talk about the country level. And they set limits about emissions factors typically that power plants are allowed, that are required to meet. In other words, that's the allowable emissions per unit of fuel combusted or generation. The pollutants that are covered under this, the emission standards in different countries, we've already started to collect those, and it varies per country, but it does include most of the pollutants that we are concerned about. And I'll, in another slide, talk about the specific pollutants we're concerned about. The uncertainty just on a qualitative scale is medium level. It's certainly a little bit more uncertain than if we were to measure emissions directly. And that's because emissions, real emissions, can sometimes be less than the emission standard, and sometimes can be more than the emission standard. And in either case, if we're assuming the emission standard is met, we're either overestimating emissions or underestimating emissions. A third approach that can be used is something that is a lot more challenging because it has more characteristics, more parameters that you have to collect data on, and that's taking what's called an uncontrolled emissions factor and then trying to take into account the use at a power plant of an emissions control device or strategy. This could be a particulate, it's called a particulate filter, what's called a baghouse filter, that would then filter out some of the particles before being emitted to the atmosphere. That's an example of a control technology that's installed on many facilities in the US. And there's a certain efficiency at which they can capture those particles. And through the parameters that I list in the description cell, we can get to an effective emissions factor. You can cover all the pollutants that are of concern in that, but the uncertainty is relatively high because we don't always know for every single plant and every single smokestack what emissions controls are there, how well they're working or whether they're working, and then get to the effective emissions factor. It's also very time consuming. So Karin, if you hit the next button, you'll see that this is the approach that we are planning to use and have started to develop the data inputs for, is by identifying the standards that are mandated within every ASEAN country. Next slide, please. So which pollutants are the most important? This answers the question of what for the emissions inventory. What pollutants are emitted? We care about many pollutants that, as Professor Hill described, can lead to the formation of PM2.5 in the atmosphere. Sometimes PM2.5, or fine particulate matter, is directly emitted. But also it can be formed in the atmosphere through chemical reactions of other, what we call primary pollutants. Those are the ones that are directly emitted. So nitrogen oxides, volatile organic compounds, sulfur dioxide, and ammonia are 4 such directly emitted pollutants. They're not particulate matter that's directly emitted, but they form particulate matter in the atmosphere through chemical reaction. And we've included in sort of a qualitative comparison across the 3 main fossil fuel types and to their relevance for particulate matter formation in the atmosphere. Pollutants, PM2.5 is directly emitted from coal power plants, not really much at all from gas power plants, and only to some degree for diesel power plants. NOx, on the other hand, is a greater concern than directly emitted particulate matter for gas plants. It's still relevant for coal, and it's still relevant for diesel. And then you can go down the list. So these are the pollutants that we are most concerned about, and their relative importance compared to the different types of fuels that are used. And with this knowledge, we can help to focus and prioritize our efforts in developing these, identifying emission standards, and in developing the emissions inventory that are country specific, that are specific to particular fuels that are used in the power sector in the ASEAN region. Next slide. So another question we have to answer is how much of each pollutant is emitted in developing an emissions inventory relative to the AIMS 3 scenarios. So here again, as I mentioned before, we're looking at the emission standards because that's the best data that we think that we have available to us to make these estimates. So with significant input and effort on the part of colleagues in ACE, we've been compiling emission standards that are applicable to coal, natural gas, diesel power plants, and to some degree, biomass or biopower plants in the ASEAN member countries. These standards are often segregated by plant capacity. If you're over a certain capacity or megawatts of plant size, 100 megawatts or 50 megawatts or 500 megawatts, could be different levels of segregation that would then allow certain amounts of pollutants to be emitted. Sometimes they're segregated by year of commissioning. Older power plants are typically given greater leniency on these standards. Sometimes they're also segregated by location. It might depend on whether you are in an urban area or whether you are in a other sort of area with a protected status. The pollutants that are covered under these standards are typically NOx, SOx, and particulate matter, directly emitted particulate matter, sometimes other pollutants like carbon monoxide and others. So we're still in the process of collecting all these standards. After reconciling the data from different sources, we will then harmonize those, choose the ones that we think are, in our understanding, the most up-to-date and accurate, And then we hope to be sending them to in-country experts and others coordinated through ACE for verification. The goal being to agree upon the most representative emissions factors based on current emission standards to be used in the study's emissions inventory. The next slide. The other part of how much is not just the emissions factor, but if you remember that conceptual equation that we put up, there's also the activity data. Here we're talking about activity for the power sector, and we're only concerned here with power sector sources that emit air pollutants. Solar facilities don't emit air pollutants during their operation. Wind facilities do not emit air pollutants during their operation. Geothermal facilities generally don't. There could be some CO2 emissions, but again, we're not concerned here with this model with tracking the greenhouse gas emissions. That's actually already included in the AIMS-3 scenarios or analysis, a report that I think is being compiled now. But here we're concerned with the emissions that are going to be forming particulate matter. So we are working with our ACE partners to receive hourly data about the electricity production by different fuel types in each of the ASEAN countries that has been done in the AIMS-3 modeling for all 4 scenarios. And of course, the list of the countries in the ASEAN region are here. You all are well familiar with that. And the emissions and the air quality modeling, as I said, will only consider the fossil fuel plants, which is coal, gas, natural gas of different generation power plant designs, diesel fuel oil, and if available, biopower. Biopower is often considered a renewable resource, especially in the context of greenhouse gas emissions, but it does emit air pollutants because it is combusted, and it can lead to the formation of particulate matter. So if available, if we have biopower, then we will also attempt to evaluate the emissions that come from biopower sources. Okay, next slide, please. The final characteristic that we need for an emissions inventory, we need to know what pollutants, how much of each pollutant is emitted, and where the pollutant is emitted. So for the where, the AIMS-3 scenarios are looking at the country level generally. For a few countries, there are several nodes that are being evaluated, but not to the level of specificity of location that one's concerned about when one is considering air pollutant emissions and the people that are exposed nearby to those smokestacks and to the concentrations that they would be experiencing. So we need to have more granular data about the location of power plants. Since this data is not coming from the AIMS-3 modeling, we have to get this data from somewhere else. So we've identified several different global databases of the location of fossil fuel power plants. And this is one depiction from one particular database called the Global Energy Monitor, updated in July of 2021. So I would say quite up to date. And you can see the location of these facilities for coal plants and for natural gas-fired power plants. If there is additional data that we can obtain from ASEAN member states or from ACE, then we'll see what we can do to utilize that. There's always the consideration when one has to do this kind of modeling that there's an advantage to using a single source rather than multiple sources, if only because then you don't have to worry about merging databases, potential duplication, potential missing sources, potential overlaps, and other considerations when you have multiple databases. But we are nevertheless quite interested in learning if there is additional data that could be made available to us about the location of power plants. But this is the depiction of the best data that we have been able to find from a publicly available source. Next slide. Okay, so now we have maybe 5 minutes or so if there are some questions now on the emissions inventory side. I see one that came in the chat, and I'll read it out. Does the emissions estimation conduct according to combustion technology? Subcritical, referring to subcritical coal. Ultra subcritical, I think, is maybe the abbreviation for USC, et cetera. It does differentiate by major fuel type, as in coal versus gas. The AIMS-3 scenarios will have some degree of sub-designation. I'm actually, unfortunately, not familiar enough to know how to answer the question specifically, but it does have some sub-designation of combustion technology. So for instance, the ones you mentioned might be the ones included to differentiate amongst coal combustion technologies. And the emissions factors likewise can in some cases differentiate by coal combustion technology. So I hope that answers that question. Don't see any others. Lamai, you still have your hand raised, and if you would like to speak, then you can unmute yourself. I know sometimes it's hard to find all the different mutes on a screen. Meanwhile, another question came in, so let me answer that first. I think if the AIMS-3 team and the NREL team refer to emission standards, it depends on the applicability year of each standard in each country. Each country has updated it. The team must be careful of different technologies with different CO2 equivalent emissions. So I agree with everything up to the end. Again, we're not doing a greenhouse gas emissions inventory. We're rather doing an air pollutant emissions inventory for those air pollutants that are relevant to the direct emission or the formation of particulate matter in the atmosphere, because that then connects to the health effects that we're concerned about. CO2 equivalents don't directly lead from direct exposure to premature death, which is the outcome that we'll be calculating. Yes, we do understand that emission standards can change. We do understand that emission standards do depend on the year of commissioning of certain plants. And I will emphasize again in the next session that we hope we've been working very well and feel very well supported by ACE. But ACE is a research institution that's not based in every country. And therefore, we hope that the ASEAN member states that support ACE will also provide some of their experts to review the compilation of emission standards that we've developed to ensure that they are the most up-to-date and the most accurate. Okay, without another question, we'll leave a little more time at the end. And again, I offered to stay on if people want to discuss more in a small group, but I'll move on to the next session. So we're just going to, in one slide, wrap up and talk about some of the next steps. Okay, so just to summarize, the project time frame is that the research in the report will be complete by June, end of June 2022, with an opportunity to learn about the results in the February to April timeframe of 2022, alongside a workshop that will, a separate part of our workshop at that time period, that will be given by NREL and our collaborators at the University of Minnesota to train on the global INMAP model. So those are our outcomes, and that's the timeline that we're working on. We'll, of course, be working very closely with ACE in between. So what we hope that you will do is when you close your browser, apparently you will be then, some sort of dialogue will appear on your screen, asking you to complete a short feedback survey about the webinar. We would appreciate if you would take the time to fill that out. It should not take you more than a few minutes. We ask that you please support us. I'm not sure from what countries our attendees are coming from. I'm not sure of your status relative to membership of the ASEAN member states and their representatives at ACE. But I hope that because you've taken the time to learn about this and express some interest, that you might also be willing to help us by reviewing the emissions regulations in your country. So again, we are very sure that they are the most up to date and that they are the most accurate that we can use for the study. Lastly, if you are interested in learning more about the applicability of the global INMAP model, the intervention model for air pollution, that's being developed from the University of Minnesota and our colleagues, Professor Jason Hill and Dr. Sunil Thakrar, and the study approach that can be applied to maybe other sectors, other scenarios, and specific countries or regions, feel free to contact us. And if we move to the last slide, you will see 2 email addresses. If you would like to contact us about the study, you're welcome to contact me. I'm the principal investigator at the National Renewable Energy Lab for the study. And if you'd like to ask more questions about the global INMAP model, you're welcome to contact Professor Jason Hill of the University of Minnesota. And we have some minutes before the hour-and-a-half allotted for this workshop. Happy to take questions and have some discussion now. If there are no more questions, then anyone is free to leave when they need to and would like. But happy to stay on and discuss things more openly. You could welcome to unmute your microphones or continue using the chat. Benny or Scott, if you wanted to say any words of closing, you're welcome to now as well.
Hey, Garvin, I'll just again reiterate my thanks to you, the team, the entire team there at NREL, University of Minnesota, as well as our partners at ACE. Again, this is a very exciting and important project. I'm honored to be a part of the team from here in Bangkok. And yes, I echo your encouragement for greater collaboration and information sharing to make this effort as powerful and meaningful as possible. So thank you all.
Thank you, Scott.
Gavin, just to echo what Scott mentioned, that we will continue the collaboration. I mean, ACE will continue our communication as well particularly with the HAPA member state as part of our AIMS-3 working group members and also other related institutions in its 10 countries to collect the data. As we also believe this is a very important study. I mean, we are working on this ASEAN interconnection master plan studies, addressing many issues, energy security, more renewable energy, but this is also the important topics that are being addressed by the minister on the improved air quality. So and again, as you say, that we welcome the involvement for everyone. I mean, feel free to contact Garvin or myself as well. Everyone would like to also be involved and provide your contribution. We'll be happy to welcome everyone to be part of it. So thank you, Gavin. Thank you, Scott, as well, and all the team.
Thank you so much, Benny. ACE has been a wonderful collaborator. I really appreciate all the assistance that your team's provided. I'm not seeing more questions come in the chat. We can wait another minute or so. Again, please feel free to unmute your microphone if you want to just ask a question directly, verbally.
Hey, Garvin, maybe I can just, this is Scott, maybe I can just add one more question to you and the team there. Is there a way to kind of ground truth the findings, the results of the model with empirical data that may be collected and available in the region from the ground? Is there a way to cross-check those two data sets?
Yeah, I mean, I'll comment on one maybe aspect of that, and then maybe I'll ask Sunil or Jason to perhaps discuss how the model was developed, because I believe that there is that kind of ground truthing. The challenge with doing any forward-looking study that might have policy or other relevance is that we can't ground truth the future. And these scenarios are meant to alter the current condition. And so all we can measure as far as ground truthing is the current condition. And of course, in data that's been collected in the past, we can also look to the past. But we can't look to the future to do that. So the role of ground truthing in air quality modeling in particular, because air quality modeling is really by design intended to be forward-looking, the way to do the ground truthing is when you develop your model, and in doing the development of the model to ensure that the model is as accurate as intended for the purpose of the model. So maybe I think Sunil, you turned on your video, so I assume you'll augment that answer.
Yeah, thank you. Thank you, Garvin. Thanks, Scott, for the question. So I agree with everything Garvin said, and I just wanted to add that Global INMAP has been evaluated. So as Garvin said, it's difficult to evaluate how well an air quality model does experimentally. But what you typically do with these sorts of models is you run them on total emissions, and you predict, you see how well the model predicts past measurement data. And so we've done this for INMAP. We have a paper that's been submitted to a journal and is currently up as a preprint, where we show these results. We've also done, of course, doing this isn't the intended use case of INMAP. INMAP is intended to be run on changes in emissions from policy scenarios. So what we've also done is we've done model-to-model comparisons, where we run Global INMAP on changes in emissions, and we compare how well INMAP does, Global INMAP does with GeoSChem or other models. So this is something we've also done and looked into.
So there are very stringent standards for models in the United States that the core or the base INMAP model, the one that's domestic for the United States, has also been evaluated against. This global INMAP model, like Sunil said, is they're continuing to develop and enhance it now. But once this paper is through peer review, it would be considered something then that has passed the scientific rigor of the peer review process and would be documented for the two kinds of comparisons that Sunil spoke about, comparisons to historic measurements and comparisons to other models that are better known in the community and are considered state of the science models.
Got it. Thank you, guys.
Yeah. Okay. Well, thanks, Lamai. I see you wrote a chat that that you're good with your questions. Anyone else? Emil, a question for you. Emil, do you see the question?
Oh, sorry. The question, yeah, I see it. Where can we download the Global INMAP? Is it available online? Yeah, so maybe I'll share a link with the GitHub page for the model. Do you think that's a good idea? Let me just find it.
Yeah, sure.
So this is the model. It's the same. It's the same model. This is for US INMAP, and then we have additional data to be used at the global scale. But this is the source code for the model if you want to download it.
Thank you. Okay, well, I think that it appears we might have answered all the questions we received. You have on your screen that you can write down the email addresses if more questions arise. And we thank you for attending. I hope you will fill out the survey that will appear on your screen when you leave this workshop. We wish you a good rest of the day, and I hope that you maintain your interest in the study for the period of time it takes us to complete it, and to be able to report back to you the results that you and perhaps other colleagues will be able to attend the workshop we plan in the early part of 2022. Thank you again to our sponsor, the U.S. Agency for International Development, and our partners at ACE. Good day to you all.
Thank you, Garvin. Thank you, everyone.